In this video, we'll do an example where we convert a nested quantifier statement to words. So our example says, let the domain of x and y be SCU students. Let L of x comma y be x likes y. And I want to convert the following logical statement to words. So this says, for all x, there exists y such that y is not equal to x, and it's not the case of it's not the case that L of y comma x. So it's not the case that someone likes someone. All right, so let's break this down. So I got that for all part first. So that would be, well, for every student x, or I could say for every SCU student x, there exists. So there is a student y. There is a student y such that, I'm going to abbreviate that as s dot t dot, such that, and now there's two parts to this and statement, such that y is not equal to x, which I can write as y and x are different. Y and x are different. They are different, and then I have this. It's not the case of L of y comma x. So that's saying that, so without the negation, this would be saying that y likes x. So with the negation, this would be saying that y doesn't like x. Okay. So I'm just going to rewrite this using some simpler language. So again, it says for every student x, there's a student y such that y and x are different, and y doesn't like x. But I think it's simpler to write this as for every SCU student x, there is another, that's how I'm going to specify different. There is another SCU student. There's another SCU student. In fact, I can make this even a little bit simpler if I don't write x here. So for every SCU student, really going to just try to use common language. For every SCU student, there's another SCU student who, and I need to somehow represent y doesn't like x. So that other one doesn't like the first one. So there's another SCU student who doesn't like them. Let me write that better. Who doesn't like them. So for every SCU student, there is some other SCU student who doesn't like them, who doesn't like that first one. Okay, so I'm going to put this in a thought bubble. Okay, so I want to end this video by looking at a very similar looking proposition where I've just changed the and operator to an implication. Why isn't this the same? So the only difference is this and has become this implication operator. And one of the things that I would think about when I compare these is, what does it take for an and statement to be true versus what does it take for an implication to be true? For an and statement, both parts have to happen. Both parts have to be true. So y has to be different, not equal to x. They got to be different. And this part, y has to not like x. For an implication, both parts don't necessarily have to be true. Like we've seen that if the if part is false, that automatically makes the whole thing true. So that's going to give me an idea here. That's going to give me an idea. I'm going to consider the following scenario. Is there kind of a simple way where I could maybe make this first part be false? Well, consider if there's like one total SCU student, which is a little bit weird, but imagine a world where that was the case. There was just one total SCU student. And if that was the case, this statement that y is different from x, that would be false, because there aren't two students who could be different from one another. But if that part is false, that makes the whole if-then statement be true automatically. Whereas in the and statement, if the first part is false, that would make the whole and statement be false. And that's different from this part being true. So that is a definite distinction in the meaning here. And that's something that we want to look out for and be careful of.